Okay, let's dive into this. Have you ever stared at a physics equation and thought it looked like a bunch of gibberish? Well, what if I told you there's a secret code hidden inside? Today, we're going to crack it. We're going to see how one single letter can tell you the entire story of an object's motion.
So seriously, is it possible? Can one letter really map out an object's whole journey? The answer is a huge, resounding yes. You see, in physics, there's this amazing little shortcut, and the master key is the letter T, for time. Let's find out how this one little letter tells us everything we need to know.
All right, our decoding mission begins with displacement. And here's the big secret, the thing that changes everything. All you have to do is look at the highest power of t in a displacement equation, and you'll instantly know what's up with the object's acceleration. It's pretty much a cheat code for kinematics.
So let's break this code down into 3 simple levels. First up, if the highest power of time is just 1, it just says t in the equation, that means the object is just cruising along in uniform motion. Simple, constant velocity. Easy enough, right? Okay, level 2. If you spot a t squared, that's your big signal. That means you've got constant uniform acceleration. And finally, if you see t cubed or t to the 4th or anything higher, well, that's when things get really interesting. You're dealing with variable acceleration, where the speed up is itself, speeding up.
Think of this table as your new best friend. Seriously, it's the ultimate cheat sheet. Look, on the left, you've got the type of equation. In the middle, you have the most important part, the highest power of t. And on the right, it tells you what that means. So a linear t, boom, zero acceleration, uniform motion. A t squared, bam, constant acceleration. A t cubed or higher, you got it, variable acceleration. It really is that straightforward.
Okay, you've got the secret code for displacement equations now. You're probably feeling pretty good. But hold on, because here comes the twist. And you're gonna wanna listen closely to this, because it's a pro tip that'll help you avoid a super common trap on exams.
And here it is, the big warning. This power of t rule, it works like a charm. But, and this is a big but, it only works for displacement-time equations. I'm going to say that one more time because it is that important. This secret code is exclusively for equations that start with s for displacement. Whatever you do, don't try to use it on velocity equations.
And this slide right here shows you exactly why. Let's put them side by side. On the left, we know our rule. If displacement s has a t squared in it, we have constant acceleration. We've got that down. But now, look to the right. The actual velocity equation for that very same motion is v equals u plus at. Do you see it? Velocity has a plain old t in it, not t squared. That's the trap. You can't just apply the displacement rule to the velocity equation. They speak a slightly different language.
So let's lock this in and look at the correct velocity equations for each motion. For uniform motion, velocity v is just a constant number, no t at all. For uniform acceleration, the equation is linear, v equals u plus at. And for that wild variable acceleration, well, that's when you'll see velocity equations with higher powers, like t squared or even t cubed. See the pattern? The power of t in the velocity equation is always one step down from what it was in the displacement equation.
All right, we have totally cracked the code for equations. So now, let's see what this all actually looks like. Because displacement time graphs, they're awesome. They tell the whole story of an object's journey, all in a single picture. And the shape of the line? Well, that's everything.
Let's start with the absolute easiest one, zero acceleration. On a displacement time graph, this is just a perfectly straight line. And why is that? Well, the slope of this graph is the velocity. So if the slope isn't changing, if it's a straight line, then the velocity isn't changing. No acceleration. This is the picture of our s is equals at plus b equation.
So what happens when you add some positive acceleration? This is our t squared situation. The graph stops being a straight line and starts to curve upwards. It looks kind of like a smile. If you were to check the slope at different points, you'd see it getting steeper and steeper and steeper. A steeper slope means a higher velocity. So that upward curve is just a visual story of the object speeding up.
And you can probably guess what happens with negative acceleration, right? Or deceleration. The graph does the exact opposite. It curves downward, kind of like a frown. The slope here gets less and less steep as you go, which means the velocity is dropping. The object is slowing down. It's just such a cool visual way to see the physics in action.
Whew. Okay, we've covered a ton. Equations, that tricky velocity rule, the graphs. So now, let's pull every single piece together into one final awesome slide. This is it. Your ultimate summary, your master key for decoding motion. And there you have it, the whole shebang.
the complete motion decoder. For every type of motion, uniform, uniformly accelerated, and variable, this cable lines up everything you need. The key feature of its displacement equation, the right velocity equation, and exactly what its graph looks like. This right here is your main takeaway. If you can master this table, you'll be able to read the story of any object's motion, no matter how they throw it at you.
So, the secret code, it isn't so secret anymore, is it? Just by looking for the power of t, you've unlocked a way deeper understanding of motion. And that just leaves me with one final question for you. Now that you know how to read these equations like a story, what other secret codes do you think are out there, just hiding in the language of science?